afternoon all. It's 6 p.m. The class is scheduled between 6 to 8. I will wait for a couple of minutes and see if people join. Otherwise, I will start and upload the session. Me too. Okay, I think we can start. People can join in between also. Let me go to the slides. Okay, let's start. Hello everyone, welcome to the course Sensors and Actuators. This is live session for the week 8. So let me introduce myself first. I'm Ananya. I'm a PhD scholar in the Department of Electrical Engineering, IIT Kanpur. My specialization is microelectronics and VLSI. So I will be the TA for this session. So I conduct this session on every Tuesday between 6 to 8 p.m. And the main purpose of this live session is the main purpose for this live sessions are to solve problems and clear your doubts. So the sessions will be useful if you join and clear your doubts in the session itself. I also record the session and upload on YouTube, but it will be useful if you join and clear your doubts during the session itself. And I will try to answer your questions in the session itself, and if for some question I don't have the answer, I will try to answer in the next session. Okay, so in general, in this live session I first briefly discuss the topics those were covered for this week. So this is week 8. So I will discuss the topics those were covered in this week, and then I go to the problems and solutions of that. So in this course, we don't have many numerical questions like other courses of NPTEL where live sessions are conducted. I have done also, like I did live sessions for a few other courses. There we mostly solve numerical problems and few theoretical questions, but for this course we mostly solve theoretical questions. And there are many like lab classes for this course as well. I will not discuss much about those lab classes because you have to go through those videos and then you will learn. And if you have any question, then you can ask in the discussion forum. I mainly focus on the theory topics, like the theory classes for this course. Okay, so let's go to the topics those were covered in this week. So the first topic that was discussed was on photolithography. So we have already discussed photolithography many times in this course, but a few key points were discussed in this week, okay, in the first lecture. So we will go through that again. So what is photolithography? It is basically patterning technique. So we create fine features on our structure, on our surface, on our wafer, using a chemical called photoresist. Okay, so this is to create patterns, and then we go for etching and other techniques so that we get patterns of thin film. So as I discussed earlier, that in microfabrication we have like different fabrication techniques. There are different techniques involved. One is deposition, where we using this we deposit thin film, like that will be a uniform thin film. Then if we want to make pattern of this thin film, like some structure of this material, then we go for photolithography and etching, and together we achieve patterning of this thin film. Okay, so photolithography plus etching, this gives us patterning of thin film. Of course we have to do deposition prior to this or during this process. Like after photolithography also we can go for deposition, and we can do the etching part, okay, wherever we don't need the film. Okay. And this is one of the main like component of microfabrication. Anything we want to do, whether it is a micro sensor or any other micro device or other electronic devices like MOSFET, we always do photolithography, and often multiple steps of photolithography is required to create a device or a sensor. Okay, for example, we know that when we want to make a sensor that is like a resistive or impedance sensor, then we need an interdigitated electrode, right? So to make that electrode, interdigitated electrode, we do a photolithography. Again, many times we need to provide certain amount of energy for the sensor to operate, for the operation of the sensor. So how we provide that energy? We make a heater and we like make a connection, like electrical connection, and through that heater, because of the joule heating, with that energy is provided for the reaction to happen that is necessary for the sensing application. So we need to make interdigitated electrode, and we need to make a heater for the same sensor. So in that case, we will need multiple steps of photolithography, one to make a heater, one to make the interdigitated electrode. Okay, and in case of devices, you know, if you are from electronics background, to make a MOSFET we need multiple levels of photolithography for to make a MOSFET or a MOSFET with circuits like an inverter or other circuits. Okay, so often one photolithography process is not enough for a device. We go for multiple steps of lithography, and what we need in that case is that our first step of lithography should match our second step of lithography, and so on. So we need something called alignment. Okay, so that means, suppose you have this silicon wafer, say, and you have a heater pattern like this here, and you have an insulating layer, because you cannot make the interdigitated electrode directly on top of the heater. So we will have an insulating layer here, and on top of that we will make the interdigitated electrode. Say now, for some reason we want our interdigitated electrode to be exactly like, say, this first electrode should be exactly on top of this pattern. Okay, and this one is on top of this pattern. Then we have to do proper alignment between the first litho step and the second litho step, and that is very critical. So alignment is one of the most critical part in photolithography. Okay, so specific instruments are there, some kind of optical arrangement on that, so that we can see, like, the first step of litho, and we can do the second step of litho on top of that. Okay, so there will be lenses, microscope, and other arrangements so that we can do it properly. Okay, now what are the other steps of photolithography? So we start with wafer cleaning. Just give me a second. We start with wafer cleaning. Now it depends on the type of wafer we are using and whether already there is a pattern or not. So we will do the cleaning accordingly, but the basic thing is that we will start with a clean wafer so that there is no contamination on the wafer, and there will be no particle on our photoresist layer. Okay, otherwise the adhesion between the wafer and the photoresist will not be good, and there will be like big particles. And you know that when we want to make features in micron sizes, if there is a dust particle of micron size, and that will affect our performance in other parameters significantly. So we start with a clean wafer. In case of silicon, if we are using a silicon wafer, then we can go for RC cleaning and other solvent cleaning as well. Next step is pre-bake and primer coating. So what is a primer? In case if we are using silicon wafer, then it is HMDS. So why we need this step? Because it improves the bonding between the photoresist and the wafer. Okay. It makes the surface hydrophobic so that there is no moisture on top of our surface. Okay. Then the next step is photoresist coating. Fourth step is soft bake. So in this week, in the first lecture, so we were the professor mainly discussed about this photoresist coating and soft baking process. So I will discuss bit more about this. So here you can see this is a spin coater using which we can do photoresist coating. So this has this jug you can see here, and we will place our wafer on top of this jug, and there will be a vacuum pump connected to this system, and that will, when we turn on the vacuum pump, so the wafer will be it will be like sucked by this jug, and it will be hold properly, like it will not move. Okay, so that is the first step. We start with the clean wafer, we'll do the pre-bake and primer coating, and then we will place our wafer on this spin coater, and we'll hold like there should be a proper vacuum between the jack and the wafer. Okay, now you can see here this jack is of a certain size. Now if your wafer is big, then you will need a bigger jack, and depends on the wafer that you are using. Okay, and we will try to place our wafer and our sample, like so that we will ultimately get an even coating of photoresist. So we'll place it in a way that uh, our photoresist will not slide in one direction. So if we try to put it at the center, okay, uniform on all sides of the chuck, so chuck will be of this size. There might be an o-ring, okay, so a rubber o-ring that will hold the wafer. Okay, we'll try to place our wafer. If we have a small piece of silicon, say, we will try to place it like this so that the o-ring can hold properly the wafer. Okay, and how it is kept in proper place by using a vacuum pump. Okay, next here you can see the interface of the spin coater, where we'll feed the recipe. So recipe is like, we will rotate the spin coater at a certain speed for a certain duration. Okay, so it can be say between 5000 rpm to 8000 rpm. The value you can select based on the data sheet of the photoresist, and say it is for a certain duration, say 60 seconds. Okay, now we normally don't start like with very high rpm, so we do it in a second step. In the first step, we generally start with a lower speed, say 500 rpm, and this is for a few seconds. Now just don't go into the details of this, like don't look at this number. What I'm just trying to say that we first rotate it at a certain speed, and then we increase the speed to desired speed, so that we get the desired thickness of photoresist. Now what will be the thickness of the photoresist? That will depend on the speed of rotation and for how long we are rotating it, and most importantly the viscosity of the photoresist. Okay, if it's like very liquidy, then the thickness will be less. If our rpm is very high, we are rotating at a very high speed, then also the thickness will be less. Okay, so these are the things we have to consider when we go for photoresist coating. And remember why the thickness of photoresist is important, because your development time, your feature resolution, everything will depend on the thickness of the photoresist. Okay, next step is, now one more thing I want to add here is that uh, the spin coating of photoresist, the like proper spin coating is very important, so that we get like uniform layer of photoresist. Okay, now if normally what happens when we spin coat photoresist, there will be like a accumulation of photoresist at the edges of the wafer. Okay, so if your wafer is like this, the photoresist layer may be like this. Okay, you may not be able to distinguish it, but often I have observed that the photoresist layer takes this kind of a shape. Now, this may affect your photolithography process. So, what happens sometimes, what we do, we remove the edge photoresist at the edge so that we get an uniform photoresist layer in the middle of the wafer. Okay. Now, another problem that can happen, like how we actually do the spin coating, we place our wafer uh, here on the chuck, and we connect it, we turn on the vacuum pump so that it gets hold, in the proper place, and then we take a pipette and we take few drops of photoresist and drop it on top of this wafer. Okay, now there may be air bubble inside this pipette when we are actually taking out the photoresist from the bottle. Okay, that air bubble can also affect the photoresist layer, the uniformity of the photoresist layer. So we have to be careful while doing this process so that there is no air bubble comes and we get an uniform layer of photoresist. Another problem that what I have observed while using photoresist, that sometimes there may be particles, like if we keep the photoresist for longer duration, there may be some particles on the resist, there may be some dust particles on the wafer or the pipette itself. So it is very important to use a clean wafer and like change the pipette every time we use. So that is one protocol. Another thing is that we should check the quality of the photoresist, because if there is particle formation over time, it happens if there is particle formation on the photoresist, then what may happen, like your photoresist layer will not be uniform, and when you go for photolithography, your contact will not be proper. Okay, contact between the mask and the sample will not be proper, and your resolution will deteriorate because of that, and you will not get the desired pattern at the end. Okay, so these are the problems associated with photoresist coating, and many of the problems we come across while actually doing the process like regularly. Okay, uh, there is no like written documents for that, but these are the things that I have observed during the experiments that I have done. Okay, so I will write it here: common defects during photoresist coating. So one is thicker resist accumulates at the edge. Okay, and another problem is that air bubble formation. Next step after photoresist coating, the next step is soft bake. So in this week the professor discussed about soft bake in detail. So why we do soft bake, what is so write it here. What soft baking does, it improves the adhesion between the photoresist and the wafer, and it also evaporates, the process also evaporates the solvent. Like photoresist is, so this is polymer, but there is often solvent, so uh, that solvent portion is evaporated partially during the soft breaking process, and it also optimizes the light absorption. If there is solvent, there will be more scattering, because we after the soft baking we will go for alignment and exposure. So during exposure, if our photoresist layer is not hard enough and there is solvent, so there will be scattering. Also, the proper soft baking is also important, because after soft baking we will have a uniform photoresist layer that will have like different optical properties. If we don't do this process properly, then we will have a material with different optical properties, so that may also change the resolution and other things during the photolithography process. Okay, so we'll look at the data sheet of the photoresist that we are using, and whatever whatever is mentioned there, the process, whether it is at 90 minutes or 90 degrees Celsius for 1 minute or 100 degrees Celsius for 1 minute, so we will follow that. Okay, so what soft baking does, it improves adhesion. It also improves uniformity of our photoresist layer. Uh, One important thing that was discussed, it makes our photoresist etch resistant. So what it means, suppose we want, after photoresist coating, say we did the metal deposition, now we want to etch away the metal part uh, like selectively, then our photoresist should not get etched away by the metal agent. Okay, so that soft baking also improve this properties, because after evaporation of the solvent, eventually the properties of our photoresist changes. Okay, that makes it better for etching. Next, it partial evaporation of solvent. Okay, and also it optimizes light absorption. Okay, so this is about soft baking. Next step is alignment and exposure. So we have like specific machine for this. For the alignment portion, exposure we will do with an UV source, UV light source. Now depending on the wavelength of the UV source, our resolution of our photolithography will be different. If the wavelength of the UV source is less, then we will have a better resolution. We can go for like smaller dimensions, smaller feature sizes. Alignment, why it is required, as I mentioned earlier, that if we have like multiple lithography, then we want certain feature of the second litho on top of say one feature of the first litho, then alignment is very important. And we cannot do it through naked eyes, because these are in micron dimensions. So we there will be certain optical arrangement for that, so that we can like move our sample or our mask like in a very small dimension. Say you want to move our mask in few micron dimensions, so there we will be able to see that first. So we need a microscope associated with that, and then we will need some xyz xy like movement system, xy and theta, so that we can properly align this few microns. So what we do, we align our photo mask that we are using with the first litho that is already done on top of our wafer. Remember, alignment is the most critical step when we have multiple steps of photolithography. And so oftentimes we have to spend a lot of time so that we get proper alignment of our mask and our wafer. Okay. So after that we will do exposure. So you can check a data sheet of a photoresist. You will see the exposure dose will be given. So that will be given in say millijoule per centimeter square. So that will be the unit. Say one photoresist that I use that has exposure dose of like minimum exposure dose of 58 millijoule per centimeter square, and we will have an UV light source that will have some intensity, some X milliwatt per centimeter square intensity. So what will be the relation between this, how we can determine the time? We will multiply with its certain t second or minute, like it depends. Then after multiplication we should get this 58 millijoule per centimeter square or more than that. Okay. uh, we cannot expose like for less duration, less time, so we will always try to overexpose little bit so that we get proper development and proper exposure. Okay. So you know the X, what is the intensity of your light, and the time for exposure you can calculate using this relation. So this will be equal to this expression. Okay. This is given, this uh, is written in the data sheet of the photoresist. We take directly from that. Now after the exposure, what we do, we go for development. Now if you have gone through the lecture videos, you know that what it means overdeveloped and underdeveloped photoresist mean. Okay. In overdeveloped, your feature sizes will be little bit bigger than what you actually intended, and in underdeveloped there will be still photoresist layer where you don't want photoresist. Okay, they're within photoresist layer present. Now see, that is why it is very important to uh, optimize our development time for that. What we normally do, like when we try to optimize our development time for a particular photoresist, then say we want photoresist here and photoresist here, and we don't want photoresist here. So we'll start with our development times, whatever written in the data sheet, and say uh, our process is not optimized, we have certain layer of photoresist here remaining. So how we check that? Sometimes it is very difficult to see through it like directly. So we take a tweezer, say, and make a scratch here. Okay. Then if you look at through the microscope, you will be able to see the scratch. Okay. If it is a plain wafer, then you know you cannot scratch the wafer that easily. Okay. So we look for the scratch, and times like after development time for which we don't see this kind of scratch, then we are now sure that photoresist is gone from the places where we don't want the photoresist to stay, and remaining photoresist are in place, intact. Okay. That is how we optimize the process. This whole process is standard, already given in the data sheet, but sometimes we have to do it again and check all the steps properly, like whether it works or not, because sometimes the process parameters may vary like little bit, and that will affect your end result if you don't have the proper optimized process. Okay. Now after development we go for hard baking. Now this process may be optional in case of many photoresist. Okay? But here given you overall all the steps. Okay. Now one more thing that was discussed was what type of mask we use in photolithography. So mask is of it can be chrome mask. So what should be the property of a mask? So, in case of photolithography, the mask should have some transparent region and some opaque region, right? In case of a chrome mask, we will have a glass or a quartz substrate, and we will have patterns of chromium that will be dark, and the glass portion will be transparent. Okay, and another type of mask is Fe2O3 on soda lime glass. So basically we want two material, one which is transparent for UV light, one which is opaque for UV light. Okay, now the problems, so you might know this, like when we are trying to go for smaller dimensions, like to make our resolution better, we are like using a different UV sources, different light sources that has lower wavelength. uh, those sources have higher energy. So for that the mask will also be different. So we have like limited material for which the we can make a proper mask, because we need two material, one for one which will be transparent for that wavelength and one which is opaque for that wavelength. Okay, so mask engineering is also important for like lower dimensions, uh, for like for smaller wavelength UV sources, for smaller wavelength light sources that is used for photolithography. Okay, so I hope till now everything is clear. I will take a pause, and there is any question you can let me know. Okay, let's go to the next uh, topic. Okay, next was a very interesting topic. So this was for lab class, but I want to discuss it a bit more because uh, first of all, I have never used this safe memory alloy, but I was very interested in the topic. I was going through the lecture videos and the lab classes. So, what it is? It's a very interesting class of material that shows some kind of memory property. Okay, now first of all, what is an alloy? Alloy is like a combination of different elements. Okay, two or more element, and one of it should be metal. In case of nitinol based SMA, so nitinol is a safe memory alloy and it has nickel and titanium. Now these are basically like phase, these are kind of phase change material. So they have two different phases. One is martensite phase. Okay, so that is normally the low temperature phase for nitinol. Now the properties in this phase will be different compared to the high temperature phase. So you know this in the structure, like the wire of nitinol wire, how it behaves at different temperature, those were discussed and shown you experimentally in the lab videos. So I'll not go into that. And another state is austenite phase, and it is the high temperature phase. And this is basically the memory state, like whatever it the shape it has in a high temperatures state, it remembers it. It go like when from low temperature to high temperature that transition happens, it will go back to its original phase. Okay. These two phases have different kind of crystal structure that basically changes the overall properties of the material at different temperatures. Okay. Now, why nitinol is an very interesting material for in especially for this course. So in this course we talk about biosensors. Often, many of the sensors that we have discussed are for biomedical application. So nitinol can be used for as an actuators for those kind of sensors, like whatever if we want to do micro manipulation, we can do using nitinol uh, based structure that was discussed already in the class. And what advantages it provides, this is very lightweight and it is biocompatible. So that is the main advantages, because when we want to use for biomedical application, this is the main criteria, that the material should not damage our tissue, not cause any problem to living cells. Okay. So this is a biocompatible material, and it has very interesting property and can be used in many areas. So I also came across about this material through this course, and I was very interested about learning this material, and I was going through some of the like uh, uh, sites and other articles in internet, like how it can be used in different purposes. If you are interested, then you can also look for it. Okay. And the transition temperature here, so in nitinol normally 50% is nickel and 50% is titanium, but the composition may vary. And depending on that transition temperature, the state change, where the phase transition happen, that can also vary. And typical range is between -50 to 110 degrees Celsius. Okay. -50 degrees Celsius to 110 degrees Celsius. And for biomedical application, it is often set, the compositions are made in such a way that the transition temperature is 37 degrees Celsius, which is the normal body temperature for our human being. Okay. So it will not affect if it is used in for some sensors and actuators mechanism in on human as well. So the transition temperature is adjustable based on the composition of this materials. Okay. Now I'm not sure what are the other types of shape memory alloy. Maybe you can look for it, and whether those will be applicable in case of biomedical applications or not, and whether those materials have any other advantages, or why it is preferred, why nitinol is preferred mostly, what are the disadvantages, that those are also you can look for if you are interested. Okay. And the next few topics were so these are lab classes, so I'll not go into the details. One is fabricated sensor on silicon. So we have discussed about the interdigitated structure, how we can make an interdigitated structure using deposition techniques and photolithography. Those things we have discussed. One such sensor was shown to you in this lab class, and how we can inspect it using a microscope, those were discussed. I think all of you have used a microscope in your school or in undergraduate class, in courses. Okay, so you know how to operate a microscope, how you can use it to see smaller features. And there are certain limitations, like the name itself is a microscope, so we can see like micron size, like relatively big, which is we cannot see like a few nanometer structure using a microscope. We should go for other characterization technique for that, like SAM or TEM. But in this course we are mostly like talking about microsensors, devices and sensors in micro dimensions, so we can easily inspect using a microscope. Now in this lab class, one interesting topic was discussed. I wanted to discuss briefly, that was e-beam lithography. So as I mentioned earlier, that using photolithography we cannot make like a 10 nanometer structure. Very small dimensions is not possible. And what will be the resolution of our structure, what will be the smallest feature size using photolithography, that will depend on the UV light source that we are using. Okay, that will depend on the wavelength of the light source we are using. It is something similar to, like as I mentioned earlier, I'll say I'm writing using this pen, and I cannot make a thinner structure than the tip of this pen. Okay, it's something like that, not exactly. So it depends on the wavelength of the UV light source. If we want to make a very small structure, then instead of using UV light, we will go for electron beam. Okay, we know that quantum mechanically electron, it behaves like a wave as well as like a particle. Classically it's a particle, but it has like a wave nature, as we have studied like in class 2 level as well. Now the wavelength, that will be uh, so electron wavelength will be very small compared to UV rays. You can do a calculation. Okay, so equal to C by lambda. Let me just check it once. This is for a photon, so this is for photons. We can use the Broglie's wavelength formula, which is equal to lambda is equal to h by mv, and for free electron, that will be 2m v. Okay, so I'm just giving you this formula. You already know this formula. So h is Planck's constant, m is the mass of electron, and v is so this is in ev, so this is the energy of this electron. Okay, so if you do this calculation, this wavelength number will be very small compared to the wavelength of UV light source. So we can use UV light electron beam to make smaller features. Now the problem here is that we will have like a, in case of UV source, we can illuminate our whole wafer. Suppose if we have this wafer, we have the source, and we can illuminate our whole wafer at a time. Okay, the source, the light falls like this. But in case of electron beam, the beam size will be very small. So what happens, we will do the resist coating. In case of e-beam, that will be that is called e-beam resist. We will do the resist coating, and instead of like directly uh, doing the exposure like we do in case of photoresist using a photo mask, and the whole wafer is exposed at a time. In case of e-beam resist, we will take the beam and we will move our beam like this. So this process is called raster scanning, and wherever we want to change the property of our photoresist, wherever we want the exposure, we'll expose at that portion, and rest of the portion will just scan like this. So this is like a sequential process, so it is not done in one go. So this e-beam photolithography is a slower process compared to photolithography, but the advantage is that using this technique we can make like a very small feature sizes. Okay, so if I remember correctly, few dimensions, few structures on the sensor that was shown in this lab class was made using e-beam lithography. The dimensions were very small. Okay, the next topic was this tissue deparaffinization for biomedical application. I will not discuss about this because to be honest, I have never done this process by myself, and I'm not the right person to talk about it. You can go through the lecture videos. If you have any doubt, you can ask in the discussion forum. Okay, because I have not done it, like I don't have a first hand experience for this. I like handling this kind of biological sample, so I'll not discuss much about this techniques. Okay, so that's all for the topics those were covered this week. Is there any question? I will take a pause here. If not, I will go to the questions next. No? Okay. So have you started using COMSOL for your project? So you are doing masters or PhD? Since no one is present here, if you are doing PhD, okay. So you have started using COMSOL, a design like simulation for your work? Okay, not. Yeah, it's fine. Oh, you are still in coursework. Okay. So let's start the questions. I think this question is from the previous week, but you will be able to answer it. Why is PDMS suitable for biological application? In microfluidics? So this is the question. I will wait for some time. You can write the answer. Uh, Also, the people who are watching will be watching on YouTube. So you can also try to answer while I am taking this pause. flexible and elasticity. Yes, that is a good point. But yes, PDMS is one flexible substrate, but there are other flexible substrate as well. So that is one point. Like you are correct, but what what is the main like key advantage of using PDMS? It is flexible, it is transparent as well, so that can be useful. Like it is not like fully transparent, but it is quite transparent, so we can store it. Yes. uh, so you see, it is chemically inert and it is biocompatible. So when we as I mentioned earlier, when we want to use something for biomedical application, then that is the first thing that we check, that whether we can use it with biological samples, whether it can be used for biomedical application or not. So that is one advantage. So it is biocompatible and it is chemically inert. Okay, so these are few points. I will write it down. It is chemically inert, biocompatible, does not react with biological samples. It is also flexible, which makes it useful for biological and medical application. So let's go to the next question. Which factor most influences the thickness of photoresist layer? So I will give four options: spin duration, option B is uh, wafer material, option C is photoresist viscosity, option D is exposure time. So what is the answer? uh, all. Okay, so yes, but the question is, what affects the most, what factor most influences the thickness of photoresist layer? See, the correct answer is photoresist viscosity. Wafer material, if the wafer is very kind of rough, that will affect. But mostly, the thickness of the photoresist is determined by the viscosity of the resist. So, if it is very liquidy, like the consistency is like very watery, then it will spread away easily. So that will give a very thin layer of photoresist. If your photoresist is very thick, like then the thickness of the photoresist layer will also be thick, right? Even if it's rotated at a very high speed, then also ultimately the thickness will be more compared to a like photoresist which has a very liquidy kind of consistency. So that is the key factor. Okay, even if you keep your spin duration and so exposure time basically does not have any effect, so we'll do the exposure later. The spin duration and the spin coating speed, that affects the thickness of the photoresist, but the viscosity is the main key factor that determines the thickness, what will be the expected thickness of the photoresist. And you know why the thickness of the photoresist that is important, as I mentioned earlier, that our exposure, our development time, and what kind of resolution we can get, that actually determined by the thickness of our photoresist. If our photoresist is very thick, so we have, this is our substrate, and if our photoresist is very thick, when light will incident through this layer, so that will actually scatter a lot, so our resolution will not be that good. But if we have thin photoresist, then our resolution can be better. But then again, you have to keep in mind that, so sometimes we go for etching and we do this process called lift off. So what we do in lift off, I will explain briefly. So we have a photoresist pattern, say photoresist here and here, and certain photoresist are mainly for lift off, so that will create like a inverted kind of pattern like this. And after making this pattern, so this is our photoresist, remember this, we coat with metal. So our metal will be here, say we do like thermal evaporation or e-beam evaporation, we'll coat this metal. Say if we want to make an interdigitated electrode, next thing what we do, we dip this wafer in acetone solution. Now you know that photoresist will be etched away by acetone. Okay, now we make our structure like this. The aspect ratio here is different. So this is our wafer. Our photoresist is actually thick. Okay, and our metal is very thin on top of this. So this is our metal. Okay, so what we do in lift off, we do this, dip this in acetone solution, and acetone will go like this. It will remove this photoresist layer, and it will also remove the metal on top of it. Okay, so at the end we will have a metal patch like this. So this is one way to make metal patterns on top of our wafer. Okay, we can make interdigitated electrode, we can make a heater very easily. Now here you can see acetone has to, like, it has to go inside of this. So we want a certain thickness of photoresist. If our this thickness is say 100 nanometer metal thickness, we want say 1 micrometer thick photoresist. Okay, then only acetone will be, we will be able to do lift off process. So that thickness is important. We as I mentioned that for thinner photoresist we will get say a better, little bit better resolution, the scattering inside the photoresist will be less, but sometimes we need thicker photoresist so that we can do this kind of process. Okay, so what we normally do after, like when we get a new photoresist, what first thing you should do is that you should download the data sheet of the photoresist, and there will be one graph there in the data sheet. So this axis will be RPM, and this there will be thickness. Okay, so you know at higher RPM the thickness will be less. will move away, the liquid will move away. So that will be the, it has something kind of like a graph like this. So this is decreasing kind of. So at low rpm you will get thicker film, and high rpm you will get a like thick, less thickness. So we start with some desired thickness. We set our spin coater speed, the corresponding speed, and we do the spin coating. And after that we measure the thickness. Okay, and verify that actually we are getting that thickness or not. Now remember, I mentioned you that over the time there may be some particle formation. Our photoresist may degrade, so you may not be able to get the exact thickness as per the data sheet. So that has to be calibrated. Like if we should check it and optimize our process properly, so that whatever speed we are setting, whether we are getting corresponding thickness or not, or what is the thickness we are getting. Okay, and we decide the thickness based on the process that we are going to do later. Say if we want to go for lift off, then we need sufficiently thick photoresist layer. Also we look, like, see what is the resolution we are targeting. If we are targeting like a very fine feature, then sometimes thinner photoresist layer is a good choice. Okay, and all these things depends upon the thickness, mainly depends upon the photoresist viscosity. spin uh, Spin speed and time also affect thickness, but viscosity is the key factor. Okay, I hope it is clear. So let's go to the next question. Whoever joined now, so we are discussing in this week we are discussing about photoresist, shape memory alloy, and other few lab topics those were covered in this week. So we have already discussed two questions. Let's go to the next question. The question is similar what we have discussed earlier. So if you remember the graph that I showed you, you will be able to answer. Higher spin speeds results in a thinner photoresist layer. So whether this statement is true or false. I can mute yourself, whoever is unmute. So tell me the answer. I will wait for a minute or so that you can tell me the answer. What is the effect of photoresist layer thickness? Like how spin coater speed affects the thickness of the photoresist layer. It is true, yes. I have already given you the graph here. So, this graph you will find uh, in the data sheet of a photoresist. Okay. Uh, so, how it will be? It will have the thickness of photoresist in one axis, a y-axis, and the speed of so RPM will be written here. Okay, rotation per minute, and the typical graph will be something like this. It almost saturate at a very high rotation speed, and I mentioned earlier the viscosity of the photoresist is the key parameter that determines the thickness, and we can slightly vary the thickness based on the RPM. If the speed is very less, then the thickness will be more, and at higher speed we almost get a constant thickness, like if our speed is very high. And normally for good resolution we operate our spin coater in this region, like we normally go for higher speed. Okay, typical range is around 5000 to 8000 rpm. Okay, so the answer is true. What is how it happens? Okay, as speed increases, centrifugal force of the substrate. Okay, let's go to the next question. So this question is very simple. It's a true and false question, but the reason why I'm taking this question is that so we are learning the process, like the standard process, but when you actually go for fabrication, when we actually do the photolithography process, then there will be many problems that you came across, right? Few problems when we do the photoresist coating that I have mentioned earlier, the photoresist layer will be thicker at the edge, so photoresist moves like this, so we will get a thicker layer at the edges, so that can create problem. There may be some air bubble formation on the photoresist, so when you take out photoresist using a pipette, and then there may be dust particles that will actually sit on top of your photoresist, and you will not be able to make proper contact between your sample and the photo mask. Okay, that will also change your pattern. There will be scattering and other things. So all these practical problems actually we face when we try it by ourselves. Okay, so there are certain precautions we should take, and always like follow the proper standard protocol. Otherwise you will be able, like at the end your result will not be what you are expected, and you will never know in what process, in which step you have done the mistake. Okay, you can see here the photolithography process, the whole fabrication process, it has multiple steps, right? So here you can see there are the 7 steps. Okay, you can make mistakes in any one of this, and your end result will be different, and we have to be careful in each and every steps here. So that is why I'm taking few like keeping few questions, even though this questions looks very simple, but it's very important in case of like when we actually go for like practical, when we actually do this process by ourselves. Okay, dust particles on the photo mask can create unwanted patterns on the photoresist. Yes. This a very simple question. The answer is true. The dust particle will affect our patterns. Now, this dust particle, what I want to say is that dust particle can be on our wafer itself. Dust particle can be on the our photoresist itself. Sometimes over the time, photoresist degrades and particle formation, like some particle formation happens like in the photoresist itself. So the particle can be from that as well. And then some, if when we use our mask repeatedly, so we don't will have a mask and will have a different patterns on the same photo mask, okay, because we we don't make it like by ourselves. We give our design to someone. That person actually makes the mask for it, and when we do that, we try to like keep multiple designs, multiple devices on the same mask, okay, otherwise it will be a waste. So we use the mask regularly, same mask regularly, like multiple times, okay. If we don't clean the mask properly also, uh, that can create problem. There may be particles there, there may be residual photoresist from the previous photolithography also. So it is very important to clean everything, and the cleaning and other protocols, those are there in labs, so that those protocols will be slightly different in different labs. It is very important to follow all these things, otherwise we will never know like what we have actually done wrong. So even though in the photolithography process we only talk about the wafer cleaning, we should also think about like proper cleaning of our photo mask before loading into the mask aligner or before going for the exposure, okay. If there will be a dust particle, that will block UV light source through the on the photoresist. And if the dust particle has like, there can be scattering by the dust particle as well, so that will change our pattern, okay. If the light will be scattered in different directions, we will get exposure in the direction in places where we actually don't want, okay. So the cleaning process has to be like we need to do it very carefully and very diligently, okay, in each and every step. So this is true. And the dust can be, okay. Let's go to the next question. What is the primary composition of nitinol? Option A is nickel and iron. Option B is nickel and titanium. C is titanium and aluminium. D is nickel and copper. You can tell me the answer as well as some properties of, yes, it's B. You can tell me some properties of nitinol as well, whatever you remember from the class, or I discussed at the beginning of this class. It has shape memory effect. Yes, do you remember what are the different phases and what the name of the phases and what are the properties in different phases? The other people in the meeting also can tell me the answer. Even if you join like right now, but I hope that you have gone through the videos. I'm sorry for the background noise. It has high temperature. Okay, I will write down the properties and the answer. It's the concept. Okay. So the answer is B. Nitinol is a alloy of nickel and titanium. Okay. So it can be 50%, like normally it is 50% nickel and 50% titanium. So we discussed what an alloy is. Alloy is like composition of two or more materials. One element is metal out of it. Okay. So the properties is when heated above its transition temperature, nitinol, so this is N, okay, returns to its predefined state due to phase shift from martensite to austenite. Okay, the crystal structure is different in these two phases. I don't remember exactly like what kind of crystal structure is there for nitinol in these two different phases. So it whatever the predefined shape is at high temperature state. Okay, at low temperature, uh, it can take basically any shape, like whatever shape you want to give, but it will go back to its memory state, like whatever its predefined shape when it is heated. Okay, and also we discussed about that this transition temperature for nitinol is different. It vary depending on the composition of nitinol, the how nickel and titanium, what is the composition of nickel and titanium, and it can vary from minus 50 degrees Celsius to 110 degrees Celsius. And for biomedical application, many times the transition temperature is set to 37 degrees Celsius, that is the normal temperature of human being. Okay. Small changes in composition alter the transition temperature. So it makes us useful for many different applications. Okay, I request you to go through the video of it. The properties, those were discussed, like shown to you experimentally in the lab classes. So again, another question on ethanol. You can tell me the answer. I have already discussed at the beginning of the class. So what are the advantages of nitinol based actuators? So in this course, this material is used for micro actuations, or can be used as actuators. So what are the advantages of nitinol based actuators? So I also request you to see what kind of other materials available, what are the advantages and disadvantages. I'm not sure about I'm not aware of this much material of which has this property, but if you are interested you can look for it. So what are the advantages of nitinol based actuators? You can name a few. flexibility. Yes. We can bend and give different shape. That is what flexibility implies, right? Yes, that is helpful in the actuations mechanism. Like depending on the application, we can give different shapes to it. Others, what about others? They can also give you answers. I know some of you have joined just now, but already you must have gone through the lecture videos, so you can answer this. So this is supposed to be a live session, so I expect answers from everyone. Otherwise, it is just one-sided, and it's difficult to conduct the session like this. So what are the advantages? One is they are lightweight. Okay, in the video you have seen that less noisy, I think so. Maybe again I'm not sure because I have never used like by noisy, like what you mean. It will be more accurate because we are controlling it like by applying heat, and that is also through electrically, so that will be more accurate maybe, instead of some movement of some mechanical thing. But I'm not sure what you mean by it will lightweight. Oh, noisy in that sense. Okay, okay. Yeah, that can be. It's not like DC motor or something. Yeah, I got your point. Yeah, they are lightweight. They are smaller in size. Okay. The wire that was shown in the class, that is of 100 micron diameter, so that's very thin, but it can do the actuations. Okay, ultimately our work will be done with that 100 micrometer thin wire. Okay, and another advantage, that is the main advantage, especially for the topics that we are discussing, it is biocompatible. It will not change the properties of biological samples, so this is something that we want. So these are few things. Let's go to the next question then. Quiet operation, yes. Okay, yeah, I got your point. From by noisy, that is what she means. But I was thinking in terms of noise, in terms of like noise in the signal, noise in the output. Okay. So let's go to the next question. So I'll write down the question first. What is the primary advantage of e-beam lithography over photolithography. So e-beam lithography is not directly in this course on the topics, but it was discussed in one of the lab classes. That is why I am giving you this question. The process is e-beam litho process is also similar to the photolithography process, but there instead of using a photoresist, we use something called electron beam resist, and the exposure process is different. Instead of a UV source, we use electron beam source, but the exposure process is like sequential. We don't do the exposure in one go. We scan each and every area of the sample. Where we want to do the exposure, we'll do there only. Okay, the spot size of the beam is less basically. But what is the primary advantage of e-beam lithography over photolithography? Step 10 scan. Yeah, that process is called raster scanning. Okay, that raster scanning is like a very it's a very known term in case of many devices, like in characterization devices also we use this something called raster scanning. So that is like this zigzag kind of scanning. So the scan is done throughout this wafer like this. It moves along x, then slightly moves y, then again x this direction, then y. This process is repeated. Okay, this kind of scanning is done in e-beam lithography. Okay, the options for here: the faster processing time, B is lower cost, C is higher resolution, D is simple in operation. Yeah, option C is the correct answer. E-beam lithography we mainly use for smaller dimensions like in nanometer range. Suppose we want to make few nanometer devices, then we go for e-beam lithography because photolithography will not work there. The UV light source will not have that kind of wavelength. So for smaller features we use smaller wavelength, and we know that electrons have smaller wavelength. You can use the de Broglie's wavelength formula, lambda equal to hp, which is equal to h by root over 2 MeV for electrons. And if you put the values here, uh, so h is the Planck's constant. I can just give you a calculation. Just give me 1 minute, I will do the calculation. Yes, so like you can take the energy will be in some kilo electron volt. So this value is 6.626 into 10 to the power minus 34. This is in joule second, and that will be 9.1 into 10 to the power minus 31 kg for electron. And you can just take say few kilo EV of energy, so that we will convert it to joule. So we'll multiply with 1.6 into 10 to the power minus 19, and if you do this calculation, the wavelength will be in the nanometer range. Okay, so we will be able to we can actually make very small feature sizes using e-beam lithography because of the smaller wavelength of electron. Okay, you can do this calculation. I'm just did a calculation that comes in the that nanometer kind of range. Okay, so that is why we use e-beam lithography, but the process is it here you can see it requires actually faster processing time. That does not so this is not an advantage, right? So in case of UV light for photolithography, we do the exposure of the whole wafer at the like in one go. But for e-beam lithography, because we go for raster scanning, so this is a very time taking process. We have to move the electron beam throughout the wafer, and if our wafer is very weak, then the processing time will also be more. Okay, so this is one disadvantage of e-beam lithography. And the cost of the e-beam lithography system is also very high, because there will be electron beam generation, and we have to move the electron beam in a particular direction, and then we have to do the scanning. Okay, so all this arrangement and everything that makes the whole system very costly. Uh, but the advantage is the higher resolution. So as discussed in the lab class, that wherever we can use photolithography, we'll make those structure using photolithography, and when we need like very small features, for those processes only we will go for e-beam lithography. Otherwise the cost of the overall wafer, overall device development or the wafer development, that will be very high uh, if we do everything using e-beam lithography. Okay, so again the answer is C. So this is useful in case of nanofabrication. We know that we nowadays like uh, devices in nano dimensions people are making, like the foundries are making. So their e-beam lithography process is used rather than photolithography. Let's go to the next question. Again, this is from the previous class, or I don't remember from which week, but you can answer this. Is like a general question. How is PDMS typically removed from the mold after curing? So we discussed about PDMS molding in earlier classes. So we create this polymer, like liquid of this polymer and curing agent, and then we pour on the master stamp that we are using, and then we do like before that we do degassing, and then we cure it. Okay, so this is the process. Now we have our master stamp and the PDMS mold on top of it. So how we remove this? Okay, that is the question. Option A is by dissolving the mold in a solvent. If you watched the video, then you might remember this. Option B is by gently peeling off. Option C is by heating it to high temperature. Last option is by UV light. What is the answer? Option B, yes, by gently peeling it off. Yeah, that is the correct answer. And this process is very crucial, so this has to be done very carefully. Otherwise, because PDMS is like a flexible material, there may be some deformation, there may be tearing, okay, but there is no other way. If we heat, as given in the option C, by heating it at a high temperature, we know that PDMS is a flexible substrate, flexible material. It cannot sustain very high temperature. So that is not an option, and by dissolving in a solvent, that will change the properties. So often our master stamp is a kind of rigid substrate, and we peel it normally from one edge and then carefully move it, okay, because if we try to directly remove it, then there may be some tearing and deformation. So it is generally done from one side and gently peel it off to like this other side. The master mold, what it's generally made using, the master mold is generally of silicon that we make using photolithography. And also this kind of process is known as, so this is also like patterning. So after this PDMS molding, we'll get a pattern PDMS. So this is also kind of like photolithography. So this kind of process is known as soft lithography. In earlier classes, I have discussed about soft lithography, right? So there also normally PDMS mold is used, and there are different techniques of soft lithography. If you are interested, you can look, like you'll find that there are different types of soft lithographies available. Okay. So I don't have more questions for this week. So these are the questions. If you have any doubt, or if you want to ask something, then you can ask. Otherwise, we will stop this meeting. So I hope that thank you. I hope that the sessions were useful for you. And if you if you want to give any feedback, if you want something to be if you feel like something needs to be changed, then you can like tell me in the live session itself. And I hope that you are also doing your assignments. I don't know what is the deadline for submission, but you check it periodically and submit it on time. Okay. And if you have any question, then you can ask in the live session itself. If the question is related to the live session or like the general question, but if it is a very specific question related to the lab class, uh, I request you to ask in the discussion forum, because few questions I will not be able to answer. Whoever is taking the lab class may be able to answer. They will be able to answer in the discussion forum itself. There may be some time. Like, please give us some time so that we we get like enough time to check this question and tell me the answer, give you the answer. Okay. Okay. So we are saying thank you means I hope that there is no question, so we can end the session here. Thank you for attending the session. I hope the session was useful to you, and it will help like solving the questions, solving the assignment. And see you in the next week on next Tuesday, the same time from 6 to 8 p.m. Okay. Thank you.